The next topic I want to cover is search keys and ordering. We can index a table on any ordered subsets of columns in a B+ tree, but the ordering of the subsets of columns matters and is going to determine the queries that are supported. We'll go through that over the next couple slides. So think about a one-dimensional ordered index like a B+ tree that we want to use to index multiple columns. So what we're going to need to do is get the data into one ordering, one dimension from those multiple columns. And the way we do that is we order the data in what's called lexicographic order by the search key column specified. So if we specify 3 columns to sort on in order, column 1, column 2, column 3, we're going to order the data by the first column. And then if 2 items match in the first column, we'll break the tie and order them by their second column. If they match on the first and second columns, we'll break the tie and order them by their third columns. Once we specify an ordering, then we can do a B+ tree that orders the leaves and answers queries about less than, greater than, and equal to. So as a concrete example, look at the table on the right. It is actually already ordered lexicographically by the search key age, salary. So if you look down the age column, you'll see that it's ordered, and there's a tie at 55, and in the salary column, we break that tie by ordering by salary. So lexicographic ordering, note that we order by age and then by salary. So the order in which you specify the search key does matter for the ordering of the data itself. So to be a little more explicit and careful, we'll make a definition. A composite search key on some list of columns K1 through Kn matches a query. If the query is a conjunction, that means it's the and, of some number of equality clauses, M, where K1 equals value 1 and K2 equals value 2 and ... Km equals value M. So we have M equality predicates ANDed up for the first M columns in the search key. And we have at most one additional range clause of the form and K sub M plus 1 operator value, where op is one of less than or greater than. I know this is kind of abstract, but let's just keep it at this level for a moment before we look at an example and ask, why would we say that such a composite search key matches the query? And the answer is because the query is looking things up and scanning them in lexicographic order. Basically, we do an equality lookup on the first M equality predicates to find the start of a range. And then we can do a scan on the things that are tied for those first M predicates on the M plus first predicate from lowest to highest. So we scan all the things in the M plus first predicate. If there is no M plus first predicate, then we just return all the things that match on the first M predicates. Let's look at some concrete examples to make this clearer. We'll use the table that we had before. It's over on the right, and it has a composite key of age, salary, and it's sorted in lexicographic order by that composite key. And we're going to look at range predicates, and we're going to ask if the range predicates match. And I think you'll get an intuition by looking at these examples of how to establish that and why it's important for searching in an index. As we go through this, we're going to label the rows green if they're rows that we visit that are in the range. And we'll label the rows red if they're rows that we visit that are not in the range query, but we have to visit them anyway, kind of to see if we've dropped off the end of the range while we're looking at the data. So let's look at our first example. Age equals 31 and salary equals 400. So if we do a sort of greater than or equal to query here, we start with the lowest value that could possibly be in that greater than or equal to range, which in this case is age 32, salary 400, because after all, the next lower thing, 31, 300, isn't even greater than or equal to our query. So the first thing we look at is already over the range. Oscar the Grouch is too big on the age field. And so we're done with this query. But we had to look somewhere in the index to figure out if there was nothing to return. And the one place we looked was at the first value that's greater than the query, which was Oscar the Grouch. So I think we can say that this matches the lexicographic order of the table. This query matches the table. And of course, from our definition, it matches because we've got all equality predicates, and there are equality predicates on the columns in the composite key. Here's another example. Age equals 55 and salary is greater than 200. So again, doing a greater than or equal to search, we start with Ernie Sanders here, whose age equals 55, salary equals 400, and he matches. And we look at the next tuple bigger, so we're scanning the range, and this is Donald Grump, and he's age 79, and that's too large, so we're off the end of the range. Again here, though, we looked at a contiguous set of rows in the table. Ernie Sanders is right next to Donald Grump, and we had to look at least one thing outside the range to establish that we were done looking. So this one also intuitively matches the predicate. The composite key matches the query predicate. And indeed, based on the definition we had, the first predicate, age equals 55, and we have one greater than or equal to predicate further down in lexicographic order, salary. So it matches the definition as well. And so we can see that this is a good match, and we'll mark it with a green check. Here's another query, age greater than 31 and salary equals 400. Well, let's look in the table. We can start by finding the first salary equals 400, which is Oscar the Grouch. And when we look at the next thing after that, it doesn't match anymore. So we should be done if we're doing a contiguous range search, but of course there's other places that could have salary equals 400 because we're ordered by age first and salary second. So intuitively, this doesn't match because we kind of have to bounce around in the index looking for matches on salary that are separated by potentially many tuples on age. Okay, and of course it doesn't match our definition either because in our definition, the first M predicates that we're anding together should be equality predicates, and only the last one should be a range predicate. Here, the first one is a range predicate, and the second one's an equality predicate. So it doesn't match the definition, and you get an intuition that it doesn't match in some practical sense either, the ordering of the tuples. Another example, age equals 31. So it matches our definition because it begins with equality predicates in the order of the lexicographic order. And it also is going to match here when you look at it for a greater than or equals to search. We'll start with the first match for 31, the lowest 31 age, which is Elmo Adams. He matches. And when we look further in the range, the very next tuple is age equals 32, Oscar the Grouch. So now we're over the range and we stop looking. But it's a contiguous set of tuples that we look at. So intuitively matches lexicographic ordering. So that one we'll mark with a green check. Now let's look at age greater than 31. So we start with the first thing greater than 31, which is Oscar the Grouch. And it's a greater than predicate, so we can just keep scanning to the end of the table. And we look at everything else, and it all matches, and we return it. Note from our definition, this is a special case of our definition. M, in this case, the number of predicates that we have equality selection on is 0. And the M plus first predicate is the first column in lexicographic order. It's column 1, which is age. And so an age greater than 1 query is indeed a match, both by definition, and you can see here that the way it works is we scan a good fraction of the table all the way to the end to get the answers. One more here, salary equals 300. Okay. And you can see that Elmo Adams matches and Donald Grump matches, but there's a bunch of stuff in the middle that doesn't. So we could start with Elmo Adams and we could look further down the range and see no matches, but there's other stuff to go find. So again, we'd have to kind of bounce around somehow looking for all the salary equals 300. And from our definition, this doesn't match because we're supposed to have all of the columns up to M be equality and only the M plus first column be a range predicate. But essentially what we have here is we don't have any predicate on age, and we have an equality on salary. And so you can see that's not matching our definition, and as a result, it forces us to bounce around in the table, and it's not a contiguous range of tuples. Okay, so hopefully that gave you some intuition for why the definition is what it is, why it says we're going to start with equality, and then we're going to have a range predicate, because basically we're going to do a lookup in this table, and then we're going to scan further until we hit the end of the range.